All right, so for today's talk, here's a quick outline for today's talk. First, I will briefly introduce two technologies, Graspable Math and From Here to There. These are two related technologies that allow students to dynamically engage with algebraic notations. Then I'll present some findings that show the impact of these technologies on student learning and how we use the log data from these technologies to study students' problem-solving processes. And so Graspable Math and From Here to There were developed to support students' algebraic learning and thinking. And so why do we focus on algebra? Algebra is an important foundation for many career paths, especially for STEM. And success in algebra is strongly correlated with college graduation rates and employment earnings, yet few students reach an advanced understanding of algebraic notations. And many middle and high school students struggle to understand basic algebraic principles, like which transformations are legal or appropriate, and how to convert between formal symbolic expressions and other representations. So to address these challenges, my colleagues David Landy, Eric Weitnauer, and Aaron Armar developed an algebra notation tool called Graspable Math. For the past 3 years, I've been a part of this interdisciplinary team at WPI to further develop Graspable Math. So what does Graspable Math do? Imagine solving problems on papers or in online platform. We usually see static expressions like these. Now, technology allows us to transform these symbols into digital objects that we can tap and move around. So for example, we can actually pick up and drag the 3 inside the parenthesis. We can also tap on the multiplication sign to multiply 3 and 5. So Graspable Math is this interactive application where students can dynamically manipulate the algebraic notations by performing mouse or keyboard actions that apply the transformations to the expressions. And so I have a really short introductory activity for you all to try out Graspable Math if you're interested. So I'll put the link in the chat now, but I'll also put the link again in the chat at the end of the talk in case it gets lost in the chat history. Just a really quick overview of this activity that I just shared. In the activity, the first couple tasks will show you how to use the gesture actions within Graspable Math to perform operations like tapping on the addition sign to combine the numbers, or we can drag the numbers on top of each other to combine them. And towards the end of the activity, you will also have the opportunity to apply these gesture actions that you just learned in Graspable Math to solve solve algebraic equations, like solving for x in this complex equation. So Graspable Math is developed based on theories of perceptual learning and embodied cognition. We posit that students' active experience of moving and transforming these algebraic objects, combined with the perceptual feedback of changes to these expressions, may help students attend to the important structures of algebraic notations, and in turn support their math learning and problem solving. And so to demonstrate how perceptual processes are involved in mathematical reasoning, let's try a couple of math problems in the chat. So here are the first 2 problems for you all. Here's the first one. Please solve this expression as quickly and as accurately as possible, and feel free to put your answer down in the chat box and we can talk about the answers. Awesome. I see some answers popping up in the chat box already. Thank you all for participating. All right, now here's the second problem for you. Again, try to solve it as quickly and as accurately as possible. Awesome. So I see that you all are experts of these simple math problems, and it doesn't seem like anyone got tricked by the second problem. But the second problem is actually kind of tricky, and you may or may not notice that you potentially we're slowed down by this incongruent spacing in the problem. And this problem is tricky because the spacing between the numbers and the operators is actually not following the order of operation. And then so some students may actually perform the addition before doing the multiplication because the numbers around the addition sign is closer together. And previous research has, and here are the correct answer. So previous research has shown that perceptual processes are involved in mathematical thinking and learning. And when the proximity of numbers follow the order of operation, like in the first problem here, children and adults solve these expressions faster and more accurate compared to when the proximity between the numbers do not follow the order of operation, like the second problem here. And other research has shown that engaging students' perceptual motor systems can improve their performance on simplifying algebraic expressions. For example, after using Graspable Math to transform and simplify expressions, students show improved performance on simplifying complex algebraic expressions like these, even on paper. So building on Graspable Math, my colleagues developed this educational technology game called From Here to There. From Here to There is a game where students work through problems from basic arithmetic to more complex ideas like distribution, vectoring, and solving linear equations. So in From Here to There, in each problem in From Here to There, students are presented with an initial expression that they can tap and manipulate, and a mathematically equivalent goal. And the objective is to transform the active expression to match the goal. Notice that the problem is not simply just asking students to add all the numbers together or to solve for X. They actually need to notice the pattern within the problem to reach the goal efficiently. So for example, here, we can drag the numbers on top of each other to add the numbers together. If whatever that I'm doing is not productive or leading me closer to the goal, I can always restart and retry the problem. And so here is one way, not a great way of solving the problem. I can add all the numbers together, and then I can use the keypad to decompose the number. So here we can do 5 plus 22. And notice that every action that I make actually adds a number to the step counter. So helping students to be aware of how many steps that they are taking to solve the problem, and help them to become more aware of their strategy efficiency and to try to improve their efficiency in problem solving. And see that the step counter turns red because I am not using a very efficient way to solve the problem. And in fact, that I only earned 1 out of 3 clovers on this problem because I didn't use a very good strategy or very efficient strategy. And the system prompts me, encourages me to retry the problem and try to find a more efficient way to reach the goal. And here's the link to From Here to There in case anyone wants to poke around with it. And again, I'll put the link again in the chat after the talk. So you'll have all of them in one place. And so over this last several years, I developed a body of research around Graspable Math. I've been involved in efficacy studies testing its impact on student learning. I've also used the log data to study students' thinking and using Graspable Math as a research tool to answer some basic psychological questions. And today I'll focus on the first 2 aspects of my work using From Here to There: its impact on student learning and its affordances on math cognition research. For each of these aspects, I will present one study in more detail just to kind of show an example of the type of work that I do. And I'll also provide quick overview of other related work, and I'm happy to talk more about any of these studies in greater details during Q&A if anyone is interested. So to test the impact of From Here to There on student learning, we've conducted several small and large-scale randomized controlled trials. And today I'll present one paper focusing on students' equivalence understanding in more detail. We focus on math equivalence in this study because equivalence is an integral part of from here to there. Notice that the starting expression and the goal and any active expression that you make and manipulate during the transformation process, they are all mathematically equivalent. And the transformation process demonstrates the equivalence of these two perceptually different but mathematically equivalent expressions. So in this study, our research questions were, first, do students improve their equivalence understanding after using either from here to there or problem sets and assessments for 2 hours? So we included a comparison condition that is solving traditional textbook problems in assessments, and I'll talk more about that in a minute. And second, do students in the from here to there conditions show more improvement on their understanding of equivalence compared to students in the problem set condition? So students in the from here to there condition solve problems in from here to there, like we saw earlier. And in the problem set conditions, students solve traditional textbook problems in assessments. Assessments is an online system that provides hints and immediate feedback on students' problem solving. So here's an example of a problem in assessment. Students are asked to rewrite the expression into a product of 2 factors. And there's an answer text box. Students can put in their answer. If they enter an incorrect answer, the system provides immediate feedback and say that this answer is incorrect, please try again. Notice that every incorrect answer and hidden request results in point deduction, so students receive partial credit on their problem solving and on their answer. And if they are stuck, if they don't know what to do, or if they're confused, they can always request hints on the problem to receive more support on their problem solving. And here's a screenshot of the problem with 3 hints and the correct answer. So most of the problems that we programmed in assessments included 3 hints. The first hint is more reminding students of the related concepts, and then 2 other hints that show some related worked examples to help students solve the problem. And if they are really stuck, they can also see the correct answer, enter the correct answer, and move on to the next one. So I worked with a team of collaborators and students to conduct this randomized control trial in fall 2019. In this study, we have 475 students, 6th and 7th graders, aged between 11 and 13 years, complete a pre-test that measures their math knowledge, math anxiety, and math self-efficacy. Then they were randomly assigned within classrooms at the student level to from here to there or problem set condition. Then they solved math problems matched on the content areas in 4 30-minute intervention sessions during their instructional period in their math class. Then they complete a post-test, again measuring their math knowledge and math anxiety. And the study took place between October and December of 2019 in a span of 6 weeks. And here are some items that we use to measure students' equivalence understanding from pre-test and post-test. These items were taken from Bethany Ritten-Johnson and John Start's work on algebra learning and understanding. And each item was scored as correct or incorrect. And there were a total of 6 items focusing on students' equivalence understanding. And the total score out of 6 on the post-test was used as the outcome variable, and the pre-test was used as a covariate in the analysis. So for our first research question, did students improve their understanding of equivalence after just a 2-hour intervention, regardless of the condition? We conducted a pair sample t-test comparing students' overall pre-test scores and their post-test scores. And the t-test revealed that students, regardless of the condition, show improvement on their understanding of math equivalence from pre-test to post-test. To answer our second research question on the condition effect, We tested whether students' post-test scores were significantly different between these two conditions after controlling for their pretest and their demographic variables. So we conducted a hierarchical linear model with students nested within classrooms. After controlling for their demographic variables and their pretest scores, we found that the condition effect was statistically significant. Specifically, students in the from here to there condition scored significantly higher on the post-test than students in the problem set condition. In terms of the group mean differences, this translates to a Hedges G of 0.16 between from here to there and problem set condition. Although the condition effect may seem modest, we were really excited about finding the effect because the effect emerged after only a 2-hour intervention, and this is in comparison to an established and effective technology like assessment. So in summary, we found that both intervention seem to improve students' understanding of math equivalence. And technology-based perceptual intervention, like from here to there, can provide students with conceptually rich opportunities to explore algebraic formalism. Specifically, we think that one potential way through which from here to there and Graspable Math, more in general, may support learning is that these tools provide students opportunity to develop their perceptual motor routines and algebraic notations. So after the randomized control trial in 2019, we worked to replicate and expand our findings last academic year. We just completed a larger efficacy study with over 4,000 seventh graders in Southeastern United States, and also with a more sustained intervention. So in addition, we implemented 9 30-minute intervention sessions, so a total of 4.5 hours in the span of 6 months. And we compare these intervention effects to another educational technology. Specifically, in addition to from here to there and problem sets and assessments, we also included DragonBox as another game-based intervention. DragonBox is an award-winning educational technology game that is commercially available on app stores. We conducted a study last academic year between September 2020 and April 2021 during COVID-19 pandemic. And we had 9 30-minute intervention sessions with a total of 4.5 hours spent across 6 months. We also measured students' algebra knowledge before the intervention, during the intervention, immediately after, and 1 month after to kind of track their growth and their growth over time. And here is a very, very quick sneak peek of our results of the intervention effect from this larger study. Preliminary findings with over 1,800 students who completed the pre-test and the post-test suggest that students in the 2 game-based conditions score significantly higher compared to a control condition where students solve the math problems that is the same as the one that we saw in the assessment condition, but these students did not receive the immediate feedback or hints. And with this larger sample, we were also able to explore potential moderators of the intervention effect. My collaborators, Craig Mason and Allison Liu, are leading the effort of testing the interaction between the intervention and gender, students' race and ethnicity, their prior knowledge, and their learning modality, either receiving the instruction in person or online, and how these interaction affects students' post-test scores. Remember that the study took place in COVID-19 with physical distancing restrictions, and the school district that we worked with offers students 100% synchronous in-person instruction in the school building, or they can opt for 100% asynchronous virtual instruction staying at home. And in our sample, we have about 65–68% of the students opt for the in-person instruction, and about 33–35% of the students opt for the virtual instruction. And preliminary findings suggest that actually only the interaction between intervention and prior knowledge was statistically significant. Specifically, in the from here to there condition, students with higher prior knowledge seem to benefit more from the intervention compared to students with lower prior knowledge in the from here to there condition. So even with all that work on the impact of from here to there and Graspable Math on student learning, there are still many open questions. For example, what are potential mechanisms through which from here to there improve students' math performance? And what are students' problem solving like a process like in from here to there? And how we can use the data within the technology to gain insights into students' thinking. So these questions led me to the next aspect of my research, using students' log data within the technology to further understand their problem-solving process. So to answer these type of questions, our lab has used Graspable Math and from here to there as a research tool to examine how students' actions may reflect their thinking and influence their math learning. And here I would just provide one example of using the log data to study students' problem-solving strategies. Specifically, I test whether students' pause time before their first action on the problem may be related to their strategy efficiency. I was particularly interested in students' pause time because I've done work on the relation between executive function and math, and I think that pause time may reflect students' self-regulation. And here I hypothesize that pausing or slowing down and look at the problems between the starting state and the goal state before taking your first action or jumping into the problem may help students notice the relevant details in the problem and help them improve their problem solving strategy. So remember that in from here to there, students can take any path to reach the goal, but they are encouraged to use more efficient strategy. Specifically, the step counters turn red when they're taking more than the necessary steps to reach the goal. And students can reset and retry the problems to find more efficient strategy. And to further demonstrate what I mean by strategy efficiency, let's do another quick activity to solve this math problem. So in this equation, what would be your first step? So to solve for x, what would you do first? Feel free to put your first step in the chat and we can talk about that. Great, so I see a couple of responses saying that we can divide both sides by 3. And yes, and there are actually two overarching or two kind of different approaches to solve this problem. One is using the standard distribution strategy where we can distribute the 3 into the parentheses. And if we take this first step, we'll reach the goal, we'll find the x in 3 steps. And like many of you mentioned, we can divide both sides by 3. And in that case, we can actually find out that x equals 4 in 2 steps. And so these 2 different strategies require different numbers of steps. And the second strategy is more efficient in terms of the number of steps, but it does require us to notice the multiplicative relation between 3 and 18, and that's many of you mentioned in the chat. And so what are the factors that predict or influence student strategy efficiency? Prior work such as that students' math knowledge, math self-efficacy, and math anxiety all influence their strategy efficiency. Students with higher math knowledge or higher math self-efficacy tend to solve problems more efficiently, and whereas students with higher math anxiety may use less efficient strategies on problem solving. But in addition to these factors, I hypothesize that pausing may allow students to notice the structure and the problems and plan for more efficient strategy. Imagine that if students just stop and look at the equation more carefully, they may notice the relation between 3 and 18 and know that 18 is divisible by 3. And then they can take that more efficient strategy to solve for x. Well, some may argue that maybe pause time is not meaningful, or maybe students are daydreaming or mind wandering. They're not really looking at the problem or thinking about their strategy. But other researchers have used pause time as a behavioral indicator of thinking and cognitive engagement in online learning systems. And it does positively predict students' problem-solving performance. And so in this study, we measure and simultaneously estimate the effect of pause time, math knowledge, math anxiety, and math self-efficacy to estimate their relative influences on students' strategy efficiency. And so here's the diagram of our primary research question. Does students' pause time, algebraic knowledge, math self-efficacy, and math anxiety predict their strategy efficiency as measured by the number of steps they take to reach the goal? So I used the data collected from the first study that I presented. Specifically, 285 students completed all the pretest measures and the intervention sessions, and from here to there, thus these students were included in my analysis. And we used the log data within from here to there as measures of students' pause time and strategy efficiency. Specifically in the system, we timestamp and record all student actions so we can analyze the amount of time they pause before they take their first action and the number of steps that they take to reach the goal. So for example, this student paused for 1.5 seconds, decided to add 2 and 10 together to make 12, took 3 steps, reset the problem, took another 3 steps to reach the goal. So this student took a total of 6 steps on this problem. Here's an example from another student who paused for 46.5 seconds and took 3 steps to reach the goal. You may notice that pause time varied across students and problems depending on problem complexity, and we were most interested in the amount of time students pause relative to their total problem solving time. So we computed the percent pause time by taking the ratio between pause time and the total problem solving time, and use the percent pause time as predictors in our analysis. And for the analysis, we focus on the first 20 from here to there problems that require 3 or more steps for students to complete. We did this because in from here to there, we intersperse those training activities to provide instructions on the gesture actions for arithmetic operations and mathematical properties. So those training problems look like the ones that we saw in the Graspable Math activity, the first 2 with like just tapping the addition sign or dragging the numbers to combine them. And these training problems often include videos demonstrating the gesture actions and require only 1 or 2 steps to complete. And so to more accurately measure students' problem-solving strategy and strategy efficiency, our analysis focused on these non-training problems that do not include the demonstration videos and require 3 or more steps to complete. And here's an example of that non-training problem that takes 3 steps, at least 3 steps to complete. And because students work individually to solve problems on their own pace using a device, their progress in the game varies. 75% of the students in the sample completed all 20 problems, whereas 25% of the students completed at least 10 of these problems. And because because these 25% of the students did still provide us with some data to estimate the relation between pastime and strategy efficiency, we included these students. And to account for the variations in the student progress within from here to there, we also included the number of problems students completed as a covariate in the analysis to account for that variation. And so to answer our research question, we conducted a linear regression model at the student level using the average pause time across the problems and average solution steps across the problem. And we also include the pretest assessments that we got from in the first session, and then included the number of completed problem as a covariate. And here with the linear regression model, we found that only students' pause time significantly predicted their solution steps. In particular, students who pause longer before taking their first action tend to solve the problem in fewer steps, suggesting more efficient strategy. And here's a table with all the beta coefficients and the 95% confidence intervals and R-squares in case anyone is interested in all the numbers. And so the beta coefficient suggests that one standard deviation increase in students' pause time is associated with a half standard deviation decrease in students' solution steps. Because we recorded other aspects of students' problem solving, like whether they completed the problem on their first attempt or whether they reset multiple times to reach the goal, we also explore how pause time may be related to these other aspects of problem solving. And so looking at how often students complete problems on their first attempt without resets and retries, we found that both pause time and students' algebraic knowledge significantly and positively predict students' initial completion rate. So students who pause longer or have higher algebraic knowledge tend to complete problems on their first attempt without resetting or retrying the problems again. We also found that pause time and algebraic knowledge significantly and negatively predict students' reset frequency. So specifically, students with longer pause time or higher algebraic knowledge reset problems less frequently, suggesting that they may have better problem solving process or strategy to complete problems more efficiently. So in summary, we found that longer pause time was associated with more efficient strategy as indicated by fewer solution steps, and also other aspects of problem solving like higher initial completion rate and fewer resets. And I think overall, this study shows that the relation between pause time and strategy efficiency may be robust and independent of other factors previously identified. And so building on top of this line of work on pause time, currently I have a fellowship proposal under review to extend this line of work and use the log data within the technology to further understand the microstructure of students' problem solving. For example, the study I just presented only shows the association between pause time and strategy efficiency. And it's unclear what students are doing during pause time and how pause time is associated with more efficient strategy. And I think one possibility is that pausing may be associated with how good or how productive students' first step is. And this first step may help set students up for more efficient strategy. A related direction is to combine the log data with other research methods, such as observation and talk out loud protocol, to gain insight into students' thinking and problem solving. Another future direction is to investigate the cognitive processes underlying students' actions. So for example, I think pausing may reflect students' inhibition skills, their ability to inhibit or regulate their impulses. And previous studies have found that students with better inhibition skills tend to perform better in mathematics. And using the log data and combining it with other psychological measures, I would love to test whether pausing or pause time may be a potential underlying mechanism between this association between inhibition skills and math performance that is previously identified in the literature. And I think studies like these can form a foundation for connecting the psychological theories and framework with the log data and online platforms to better understand students' cognitive processes and to adapt and develop adaptable and dynamic learning systems that support individual students. I think another implication for these type of work is that the log data can help us go beyond the correctness of students' answer at scale, and we can leverage the data within the technology to examine and support students' problem solving. So in conclusion, here's a quick summary of everything that I covered today. I introduced Graspable Math and From Here to There. Graspable Math is this dynamic technology designed to support students' algebra learning. And From Here to There is a game that we developed using Graspable Math. And I presented some impact findings suggesting that From Here to There may be an effective tool to support student learning on math equivalence and maybe algebra more generally. We think that From Here to There, what From Here to There may be doing is to help students make connections between their actions and algebraic transformations and attempt to important structures in the notations. I also presented some work demonstrating the types of considerations we had to do and had to make when using the log data to answer psychological questions, and how we can use the log data within the systems to study students' thinking and problem solving. And as an example, I showed that using the data within From Here to There, I found a significant association between students' pause time before their first action and their strategy efficiency. And I just want to mention that the work I presented here today is a part of a larger synthesis we recently wrote for the book, Mathematical Learning and Cognition in Middle Childhood and Early Adolescence, Integrating Interdisciplinary Research and Practice. In this chapter, we go more in depth about the theories behind the design of these tools. We presented additional smaller scale classroom studies on the impact of the tools and how we use the data to study various aspects of students' cognition, behavior, learning, and problem solving. We also talk more about the current development within Graspable Math Activity. It's an online platform that houses various formats of the tasks that leverage the dynamic nature of Graspable Math to support student learning and classroom instruction. And I have a few slides on other studies and a few screenshots of Graspable Math activities. I'm happy to share those after Q&A if anyone is interested. And hopefully the book will be available sometime next year, and you all can learn more about our work. Of course, I'm happy to share the preprints of the chapter or the postprint of any of the studies that I presented here. So please do not hesitate to contact me. And Erin and I always love questions and collaboration ideas, so please feel free to reach out anytime. And finally, I just want to thank the Center for Educational Neuroscience for the opportunity to share my work today, all the children, parents, teachers, staff, and schools for their participation, and the Institute of Education Sciences and the U.S. Department of Education for funding our work, and my collaborators and students for their work on these projects. And these are just a few people on the team. There are many, many more who make this research possible. And so with that, I'm happy to open it up for questions and discussions, and happy to take any feedback on our research, any suggestions for the future directions. And here's my reminder for putting the links in the chat again. So thank you so much.
Thanks, Jenny. It's a fascinating work and a really beautiful talk. So we've got about 15 minutes or so. If anyone would like to ask any questions, you can put your virtual hand up and we'll invite you to ask your questions yourself, or you can put them into the chat as well. And we can send these links through the mailing list as well when we send the video out, Jenny. So while people are thinking of questions, so I think, was it in the last efficacy study you presented, was Graspable Maths was the only one that interacted with prior knowledge. Was that right? Do you have any
Yes.
thoughts on why that is? Or...
Yeah, that's a really, really interesting question. And let me see if I can find that slide. And I think one possibility, one thing that we're thinking is that, let me see. Yes, here. One possibility is that, so in from here to there, we ground the gesture actions and transformations directly in the algebraic notation. So we use abstract notations from the beginning. And we think that in the game, students are really encouraged to solve problems more flexibly and efficiently. And so we think that the focus of the game may help the students who already have some conceptual understanding or procedural knowledge to further develop their strategy, flexibility, and efficiency. And so I think that combining the focus on the notation and the focus on the strategy, that may make from here to there particularly beneficial for students who already have some knowledge. And I think what we did by including Dragonbox is another tool that is commercially available, and their approach is completely different, even though they're still embedded math learning and problem solving in the game context. They introduce the like equation solving in this. They pretty much like hide the math in pictures, and in pictures of dragons and monsters. And so like the cards and the symbols or the pictures still move and follow the mathematical principles, like you can cancel the opposites with a positive and negative color of pictures. So they embed these mathematical concepts, but they are grounding them implicitly in pictures, and then slowly transitioning students from these more concrete or pictorial representations to abstract algebraic notations. And then so I think that may be one possibility, and the differences between from here to there and how we may see differences in the interaction.
So was the effect seen in children with higher prior knowledge? So they did better. Right?
Yeah.
All right. Interesting.
Yeah.
So I've got quite a few questions, but I'd like to open it up to other people as well. If they would, if you can raise your virtual hand by pressing on the reactions tab at the bottom. I don't know if you want to remove your sides, Jenny, and we can make it a little more social and people can turn their cameras on. Another question I was thinking about was in terms of the pause effect and maths anxiety. So is like, I'm just speculating here that I wonder if people who are anxious or have math anxiety also pause as well.
That's a really, really interesting question. And we actually thought about that.
Or some kind of thing going on there.
Yeah, and so here is the correlation table looking at the pause time. And so pause time here, and students' math anxiety. So we do see this significant but negative association. So students who pause longer actually tend to have lower math anxiety, which is kind of counterintuitive, and I still don't quite understand this association. But because one hypothesis I would have is that maybe students with math anxiety would kind of just freeze up and ended up having longer pause time, right? But the data doesn't seem to support that hypothesis. And I think that the correlation is also fairly weak, and here, especially after controlling for the progress within from here to there. And I think one idea that I have, and I included that in the paper, is that perhaps pause time, although it may be influenced by students' prior knowledge or their math anxiety, it may be capturing a distinct construct like inhibition or metacognitive skills. And that's why the correlation is actually not as strong as that we would be expecting. Another thing that I think sometimes like reviewer raise for this paper is that, well, maybe pastime is a lot of things. It may be influenced by anxiety, knowledge, your metacognition, your inhibition is a whole host of things. And I think I'm hoping that with more funding and with future studies, I will be able to bring in different research methods to better understand what students are thinking, and if there are different profiles of student behavior that to unpack this relation.
Yeah, maybe the children with math anxiety just want to get it over with quickly, so start really quickly. But there's a project at the Centre for Educational Neuroscience that you might be interested in, actually, that's to do called Stop and Think, where it's trying to train children to stop before doing maths problems. So maybe we'll send that to you and have a look. Rebecca.
Oh, yes, please.
Yes, the pause time thing I find very, very interesting, and I think you're absolutely right, Jenny. It could be for many, many reasons. So the pause time could be inhibitory control, stepping in and just going, okay. It could be, but then it could be the opposite. It could be a delay for a number of other reasons, and including intrusion, which of course would mean poorer inhibition. So it would be really interesting to introduce even just a very basic executive function measure in here to see how that correlates with performance on the maths tasks and the pause time, because I see, so I just want to make sure I understand this maths anxiety correlation correctly. So maths anxiety correlates negatively with, correlates negatively with solution steps. So it positively with solution steps. So the higher a child's anxiety, the more steps they use, or the more steps they use?
The more steps they use. And the less efficient strategy suggested.
Okay, and their algebraic knowledge is poorer. Is that? I just want to make sure.
So math anxiety
scales,
math anxiety and algebraic knowledge is negatively correlated. So as we would expect, higher math anxiety, lower math knowledge.
Okay, because there is some research, and I don't know how much it's been followed up, that children with maths anxiety, but with better working memory, their working memory facilitates the task completion when they are more anxious.
Yeah, interesting.
And then children with poorer working memory, it has the opposite effect. So there's kind of like this two paths taken, dependent on your working memory capacity. And I think it's Waters 2014, but I'm not sure, I could look it up.
Okay.
But it would just be interesting to bring in another measure, like a measure of working memory, or maybe just a fruitful or something, so that we can see.
Yeah, definitely. I will have to add it to my proposal to also include math anxiety and working memory as measures. But I love to follow up on those studies and to really starting to disentangle all these relations.
Yeah, I love this. This is fantastic talk. Thank you so much.
So I think Katrine, if I'm pronouncing it correctly, have a question. So I'll just read it to help myself read it, and for the audience too. Maybe I missed this, but what was the problem set condition exactly? Why not have compared the Graspable Math intervention to a control that is just went to a traditional classroom? That's a really, really great question. So in the first study with 475 students, the problem set control condition is this previously established and effective technology called assessments. So students solve traditional math problems in assessment. So this is more of a traditional approach of problem solving and kind of like a homework style platform. But in this in this platform, students receive immediate hints and feedback. So they can, let's see, if they answer the question incorrectly, they receive feedback, and they also have receive partial credits, and they can request hints, and there are the hints to provide some support for their problem solving. And the question about why not just a traditional classroom business as usual? And that's a really, really great question. And because in this study, we were looking at the just comparing from here to there to effective educational technology. But in the larger study where we have 4 conditions, so these 3 technologies, and then a active control condition where students solve assessment problems, just like the one that we saw earlier, but without the hints and correctness feedback. So they didn't have the hint button to request support. They also did not receive feedback on their answers. And so we think that this mimics more of a traditional homework style assignment that students did not do during like typical practice. Students do not receive feedback on their homework until much later. And we did this because in this way, we could provide all students in all conditions with a type of educational technology, but the active control is more similar to what we would typically see in like a homework style intervention. I hope that answers your question. Thank you.
We've got a couple of minutes left if anybody else has any questions. I really love the interface where you kind of move these different symbols around. It's kind of maths itself seems like a dynamic process that transformations are taking place. And so to do that on screen in a platform kind of seems like a really good way to extend what's going on, and so they can actually see the actual transformations that are taking place. And like I may have missed it, but at the beginning you were showing combining different numbers together by dragging them on top of each other, and that looks very good at or that really represents kind of like stacking numbers or combining them together. Is it the same for like dividing or like multiplying? Do you use kind of visual transformations for that, or is it the same kind, but it's the operator that goes over that changes it?
So here I'm going to hack into our system, and so in multiplication, it is really similar. You tap on the multiplication sign, and then the numbers combined and show the multiplication. In the division world, similarly, if you tap on the division sign, you can factor and like do the division. You can also drag the numbers to kind of cancel out the two. And there are also distributions and factoring. Let me see. Factoring. So in the factoring world, we have here decompose 10 into 2 times 5. And then we can drag the 5 on top of each other, get the 5 out that way.
Lovely. Thanks. That's really interesting. Okay, I think we should probably wrap up now, but thank you so much, Jenny, for a really fascinating talk and for sharing your work with us.
Thank you so much for having me.
Yeah,
thank you, everyone.
We'll distribute the recording to everybody, and we can send your links through as well, Jenny. And hopefully everyone can join us next week. It's our last seminar of the term, and have a good week. Until then, thank you.
Thank you.
Yes, stop recording.